Initial value problems. Here we solve first order differential equations with auxiliary condition y of a is equal to alpha. We know that the general form of a first order differential equation is y dash is equal to f of xy, where y dash is equal to dy by dx and f of xy is a given function. The solution of this equation contains an arbitrary constant. To find this constant, we need a point on the solution curve, or we need y to be specified at some value of x, say at x equal to a. Hence, we have y of a is equal to alpha as an auxiliary condition. Also, an ordinary differential equation of the order n is yn is equal to f of x, y, y dash, y double dash, etc. yn minus 1. This can be transformed into n first order equations y naught equal to y, y1 equal to y dash, y2 equal to y double dash, yn minus 1 is equal to yn minus 1. Or equivalently, y naught dash is equal to y1, y1 dash is equal to y2, y2 dash is equal to y3, etc. yn is equal to f of x, y naught, y1, etc. yn minus 1. If these conditions are specified at the smaller value, at some value of x, then the problem is called initial value problem and conditions are called initial conditions. It has the form y naught a is equal to alpha naught, y1 a is equal to alpha 1, yn minus 1 a is equal to alpha n minus 1. So, if the values of ya are specified at different values of x, then the problem is called boundary value problems. Let us see some examples of initial value problem and boundary value problem. Example of initial value problem is y double dash is equal to minus y and y of 0 equal to 1 and y dash 0 is equal to 0. Note that x is defined at 0. Problem is initial value problem. And the same differential equation y double dash is equal to minus y and y 0 equal to 1 and y pi is equal to 0. It's a boundary value problem because x is defined at 2 points 0 and pi. So that is the difference between initial value problems. In the initial value problem, the value of the function is defined at a particular point. That's a single point. While boundary value problems values are defined at different points. Here, x equal to 0 and is equal to pi. The vector notations are also used, and sets of first order differential equations are of the form y dash is equal to f of xy, y of a is equal to alpha, where f of xy is equal to y1, y2, etc. f of xy, column matrix. One method to solve this differential equation is Eulers method. The basis of Eulers method is the truncated Taylor series of the function y about x. It is y of s plus h is equal to y of x plus h into y dash x. This predicts the value of y at s plus h from the information of y at x. Starting with the initial values of x and y, one can move to the solutions in steps of h. The truncation of Taylor series is given by E is equal to half y double dash psi h square is a function of order of h square. H between psi between x and s plus 1. Also, the accumulated error in this one is given by E accumulated error is equal to NE is equal to xn minus s naught by h into E, which is a function in multiple of h or order of h. Note that the accumulated error is 1 or less than that of error given, or per step. Connection between this Euler function, Euler's formula, and actual value and error is given in this diagram. Then the differential equation is y dash is equal to f of xy with a dependent variable y. Now the change in the solution y between x and x plus h is y of s plus h minus yh is equal to integral s to s plus h y dash dx is equal to integral h to s plus h f of xy dx. It's the area of the panel under the curve y dash h plot. Euler's formula approximates this area by the area of cross-hatched rectangle. See, the cross-hatched rectangle is given by Euler's formula, and the area under this curve is given by the actual value, and the difference between these two gives the error. Okay. Clearly, the truncation error is proportional to the slope of the plot. Let us solve one initial value problem. Y dash plus 4y is equal to a square. Given y also equal to 1. The steps of h equal to 0.01 from h equal to 0 to 0.03. Also compute the analytical solution. Y is equal to 31 by 32 e raised to minus 4x plus 1 by 4x square minus 1 by 8x plus 1 by 32. And the accumulated truncation error in each step. So for convenience, we take xi is equal to yh and yi is equal to y of xi, so that the Euler's formula takes the form yi plus 1 is equal to yi plus yi dash h. Where yi dash is equal to xi square minus 4y. Step 1. H not equal to 0 and h1 is equal to 0.01. They are given by not equal to 1. Now y naught dash is equal to h naught square minus 4y naught. Substituting for h naught and y naught is equal to 0 square minus 4 into 1 is equal to minus 4. And y1 is equal to y naught plus y naught dash h is equal to 1 plus minus 4 into 0.01. See, y naught dash is minus 4 and the value of h is 0.01 and y naught is 1. So y1 is equal to, simplifying, you will get 0.96. And y1 exact is given by substituting for h is equal to 0.01. y1 exact is equal to 31 by 32 into e raised to minus 4 into 0.01 plus 1 by 4 into 0.1 square minus 1 by 8 into 0.01 plus 1 by 32 simplifying 0.9608. And so accumulated error is given by the difference between the two values 0.96 and 0.9608. The difference is minus 0.0008. Step 2. h1 is equal to 0.01 and h2 is 0.02. And y1 dash is given by h1 square minus 4y1 equal to 0.01 whole square minus 4 into 0.96, which is minus 3.840. And y2 is equal to y1 plus y1 dash h. y1 is 0.96 and y1 dash is minus 3.840 and h is 0.01. Simplify, y2 is equal to 0.9216. And y2 exact value is given by 31 by 30, substituting in the given function. 31 by 32 e raised to minus 4 into 0.02 plus 1 by 4 into 0.02 square minus 1 by 8 is 0.02 plus 1 by 32. It's simplified as 0.9231. And the accumulated error is given by 0.9216 minus 0.9231 is equal to minus 0.0015. And step 3, 2 is equal to 0.02 and S3 equal to 0.03. And y2 dash is equal to h2 square minus 4y2 is equal to 0.02 whole square minus 4 into 0.9216 equal to minus 3.686. And y3 is equal to y2 plus y2 dash, h is equal to 0.9216 plus minus 3.686 into 0.01 is equal to 0.8847. And the accumulator actual exact value is given by y3 of exact value 31 by 32 e raised to minus 4 into 0.03 plus 1 by 4 into 0.03 whole square minus 1 by 2, 1 by 8 into 0.03 plus 1 by 32. Simplified as 0.8869. So accumulator error is given by 0.8847 minus 0.8869, which is equal to minus 0.0022.